Welcome to the course on computer design of electrical machines. We have a lecture 29 today. So, outline of presentation with start with the introduction, modeling of brushless DC motor, design of surface mounted brushless DC motor, design guidelines for brushless DC motor, and problems of design of surface mounted brushless DC motor and references. Coming to introduction, why name the brushless DC motor? Anytime only two devices are conducting, as you can see in the figure, and current waveform is rectangular with 120-degree phase width, and the fundamental component of line current is root 6 pi into IDC. So, coming to modeling of brushless DC motor, modeling of brushless DC motor ABC frame, the back end of each trapezoidal require rectangular current, inductance does not vary with sinusoidally and not advantageous to use the DQ transformation, and so use the ABC phase variables. The voltage equation for brushless DC motor are as follows. As voltage equation for brushless DC motor are equal to VABC as a matrix, and with the element of unit matrix with the R00, 0R0 and 00R, and as a current vector IA, IB, IC, and then matrix inductance matrix LA, LBA, LCA, LBA, LB, LBC, and LC, LB, LCB, LC, and as a multiplied by current vector IA, IB, IC plus the back EMF EA, B, EC. So, now we can say here the self inductance here is L equal to LB equal to LC because of identical winding equal to L, and mutual inductance is LAB equal to LBC equal to LC equal to M, and the sum of the currents in the loop is IA plus IB equal plus IC equal to 0 at any moment of time. So, now we can say mathematical model, we can say derivative of current P into IA, IB, IC equal to 1 upon L minus M 0 0 0 1 upon L minus 1 0, and then 0 0 1 upon L minus 1 into as a vector in bracket is a voltage vector VABC minus again resistance matrix RRR with all other elements 0, and then current vector IIBIC minus the back EMF vector EA EBC bracket close, and the torque here is T equal to AIA plus EBIB plus ECIC divided by omega, and the phase currents IIBIC with 120-degree duration in each half cycle. And you can see how the circuit is there, how this with the DC applied and DC link current, and how the winding really current goes as IIBIC with the resistance of the winding and the inductance of the winding, and with the back EMF for all three phases typically. So, we can call it here now the trapezoidal back EMF is square wave current, high torque density and high torque ripple, and torque ripple square wave cause high torque ripple during the zones of overlapping commutation, and however during the conduction period should be the typically constant torque with the constant current and constant flux. So, hysteresis current control is normally used to limit the current. You can clearly see how the back EMF typically with the 2D sectional view of 24 slot 20 pole outer rotor BLDC motor, and how the back EMF of 24 20 pole outer rotor BLDC obtained from the 2D finite element analysis, and how typically the here you can see the torque waveform of a 24 slot 20 pole outer rotor BLDC motor obtained from the 2D finite element analysis, and how the current pattern for all three phases typically goes for this motor. Now, coming to typically the comparison with the BLDC with the PMSM, the type of magnet motors typically sinusoidal back EMF, sinusoidal current, and the lower torque density and less torque ripple, and surface PMSM sinusoidal back EMF and sinusoidal current, and can be made to operate like synchronous motor by leading lagging current. And you can clearly see here the typically for the BLDC, it's a you can see how the 2D section view of a 27 slot 6 pole PMSM, and how the your back EMF typically of 27 slot 6 pole PMSM with motor obtained from the 2D finite element analysis, and how you can just see the current wave, typically the torque of a 20 slot PMSM obtained from 2D, and how the current waveform this typically goes in form of with the back EMF. So, now coming to comparison between with the assumption heat dissipation capability of machine is same in both the machine, no losses in the rotor, and stereo surface area is same as both machine, and equating copper losses we have here 3 into IP1 divided by root 2 square into RS equal to 3 into root 2 upon divided by root 3 into IP square into RS, and we can say IP1 equal to 1.15 IP2. So, equating the output power we have a 2 EP IP2 divided by 3 EP IP1 by 2 will become 1.15, and where IP1 IP2 are the peak value of current in PMSM and BLDC motor respectively. So, BLDC motor is capable of supplying same power and high torque to inertia ratio. So typically constant torque till base speed and constant power region above the base speed. So angle between the phi and is angle between phi s is 90 degree till the base speed, and phi s angle is 90 degree above the above base speed, so that the phi due to stray current opposite magnetic flux. So you can have a comparison here typically for BLDC motor with here PMSM sinusoidal winding and here a concentrated winding in BLDC. Here EMF is sinusoidal, here EMF is your trapezoidal, and here we have a 180 degree conduction for PMSM, and here 120 degree conduction came of BLDC. Here the power density is 15% higher in BLDC motor, torque and inertia ratio 15% higher in BLDC motor, and speed encoder expensive in PMSM and torque ripple is less in PMSM. Now coming to typical design of surface mounted magnet brushless DC motor. The magnet circuit is the analogous of an electric circuit. Electric circuit, a flow of current, and the magnetic circuit is the flow of flux. And consider the rectangular palm magnet with the radial length Lm and magnetic flux density Bm emanating from it. And here you can see the 3D view of a simpler rectangular palm magnet. Now coming to design of surface mount BLDC motor. So magnet flux is phi m equal to Bm into m, and flux density of magnet is Bm equal to Br plus mu r mu 0 Hm, and substituting this 4 and 5 we get phi m equal to Br into m plus mu r mu 0 m Hm, and further from this equation we can write phi m equal to phi r plus rho m into Fm, and where the permeance of the magnet is rho Pm equal to mu r mu 0 m upon Lm, as you can see in the diagram. So consider a arc shaped magnet with a radial length Lm and axial length L, and magnetic circuit model assuming it to be a radial stack of different length rectangular magnets, and during magnetization the same amount of flux magnetizing each differential length dl, and the permeance of the arc shape magnet is expressed as rho m equal to mu 0 mu r into L into theta p divided by logarithmic 1 plus your Lm upon Ri, and the remnant flux of the arc shaped magnet is phi r equal to Br L into theta p into Ri, where Br is the remnants achieved at Ri and L is the axial length of the magnet, as you can see in the figure. So in common case where Lm equal to much lesser than Ri can be simplified by approximately the permeance shape as rectangular with the average cross section. So rho m equal to mu 0 mu r into L into theta p in bracket 0.5 divided plus Ri upon Lm. So the core is considered to be a highly permeable ferromagnetic material, as you can see in the figure. So because of this, flux leaving the magnet equal to the flux that crosses the air gap. So the magnet and air gap flux density are related, that is B is equal to Bm into m upon Ag equal to Bm into C phi, where Am and Ag are the cross sectional area of the magnet and air gap respectively, and C phi equal to m upon Ag, that is the ratio is the flux concentration factor. And by flux division rule, the magnet flux is equal to phi m equal to Bm Am equal to phi r into rho g divided by rho g into plus rho m, and the air gap permeance is simply modeled as rho g equal to mu 0 Ag upon g, and from this we can write phi m upon phi r equal to Bm upon Br equal to 1 upon 1 plus mu r g upon Lm into C phi, and the MF across the circuit is given as Fm equal to minus phi m upon rho g, and substituting the we have Fm equal to minus phi r upon rho m plus rho g, and further simplifying typically this equation we get Fm equal to minus Br into Lm divided by mu 0 mu r in bracket 1 plus Lm upon mu r g into C inverse into phi. So now coming to typically modeling of translation BLDC motor. So we can say rotor has a magnet separated by spacer mounted on the back iron, and the stator has back iron slots concentrating the winding. So one slot per pole per phase is considered the magnetic circuit. So the one flux loop arises out of one half of the two magnets and closes through the stator and rotor crossing the air gap. So typically coming to RR and RS reluctances of the rotor and the stator back iron respectively, and 2Rg equal to reluctance of the one half of the air gap with the compensation of slotting. So by considering RR and RS to be negligible with respect to Rg and RML, the magnetic circuit can be simplified as shown in the figure here. So now flux division. By flux division, the air gap flux is related to magnetic flux, that is phi g upon 2 equal to phi r upon 2 in bracket rho g upon by 4 divided by rho g upon 4 plus rho m dash upon p rho g, where rho m is equal to dash equal to effective length of the permeance of the magnet. And further simplifying, we have phi g equal to phi r in bracket 1 upon 1 plus rho m dash upon rho g, and the magnet permeance is rho m equal to mu 0 mu r alpha m tau lm upon lm L upon Lm, and alpha m is the magnetic fraction, and given as Lm equal to tau m upon tau p, and where P is the pole pitch and Tm is the magnetic pitch. So from the circular arc straight line method, the leakage permeance of the magnet is rho L ml equal to mu 0 L upon pi into logarithmic in bracket 1 plus pi g upon 1 divided by alpha m into tau p. Combining this equation, the effective magnet permeance is rho m dash equal to rho m plus 4 ml, rho ml equal to rho m into kml, where kml is the magnetic leakage factor and is given by kml equal to 1 plus 4 into rho ml 1 upon rho m, and substituting these, so we get the kml equal to 1 plus 4 lm upon mu pi mu r alpha m into tau p, and logarithmic in bracket 1 minus phi g upon 1 minus alpha m into tau p. An approximation of the air gap permeance is required because this flux emanates from the cross-sectional area of Lm into tau p minus 2g by p by L into L and enters a stator cross-section area length of tau p into L, as you can see in the figure. So now coming to circular straight line for fringing flux. So fringing flux is the circular arc and straight line model, and fringing flux permeance is given by rho f equal to summation of mu 0 d upon L equal to summation mu 0 L dx divided by g plus phi x, where rho f equal to 0 to x in integral mu 0 L upon g plus phi x into dx, and rho f equal to, it can be mu 0 L 0 to x dx upon g plus phi x. So further simplifying, we have a rho f equal to mu 0 L upon pi logarithmic in bracket 1 plus pi x upon g. So similarly using the same circular arc straight line method, the magnet leakage permeance of the BLDC motor is given as rho ml equal to mu 0 L upon pi into logarithmic in bracket 1 plus pi g upon tau p minus tau m, and rho ml is the further can be simplified equal to mu 0 L upon pi into logarithmic 1 plus pi g upon Tm, and the air gap constitution factor and air gap flux length. So air gap area is assumed to be average of tau p into L, and that is tau p into alpha m minus 2g into L, and ignoring minus 2g into L term, so Ag comes tau p L in bracket 1 plus alpha m divided by 2, and with the approximation, the air gap flux is air gap permeance is rho g equal to mu 0 tau p in 1 plus tau m into L upon 2g, and air gap flux is given phi g equal to mu 1 upon 1 plus rho m dash upon rho g, and further simplifying, the air gap flux is phi g equal to 1 upon 1 plus in bracket 2 mu r alpha m kml kc upon g divided by 1 plus alpha m into im into phi r, and the flux concentration factor is given as c phi equal to am upon ag, that is alpha m tau p into L upon divided by in bracket tau p into L 1 plus alpha m divided by 2, and further simplifying, we have c phi equal to 2 alpha m upon 1 plus alpha m, and we have here phi g equal to 1 upon 1 plus mu r kml into kc upon rho c into phi r, and the air gap flux density pg bg equal to phi g upon ag, that is equal to 1 upon 1 plus 2 mu r mu m alpha m kml kc g divided by 1 plus alpha m lm into phi r upon am into am upon lg ag, and for further simplifying, we get bg equal to c phi upon 1 plus mu r kml kc divided by rho c into br. So the exact operating point on BS curve is found to be computing permeance coefficient PC as a slope of this line, PC equal to minus mu on Bm divided by mu 0 into Hm, and that is equal to Lm Ag into G into Am, and this PC equal to Lm upon G into C phi. For the shape operation of magnet, the magnet length should be greater than the air gap length. And then coming to permeance coefficient, I mean, you say dimension of operating point on BH curve of the magnet. So we can say like back iron must support 1/2 of the air gap, and the back iron flux is given as phi bi equal to phi g upon by 2, and back iron width can be WBI equal to phi g upon 2 B max KST into L. There are NSM equal to NSPP into NPH slots and teeth per magnet pole, and the air gap flux from the each magnet travels through NSM teeth, and each tooth must carry 1 upon NSM of the air gap flux, and hence the tooth width is WTB equal to phi g upon NSM B max into KST into L, and that is 2 WBI upon NSM. So coming to typically modeling of the air gap inductance. So air gap inductance depends on the reluctance seen by the coil due to the flux flowing across the air gap, and the air gap inductance of the single coil or pair of the slots is given L equal to 2 alpha m upon divided by 2 in bracket Rg plus Rm, and the substituting Rg and lump magnet space reluctance with the magnet reluctance reduces Lg equal to Ns square into mu 0 L top E upon divided by 2 into Lm plus mu R into G, and the total air gap inductance multiplying this equation with the number of coils concentrated series N by 2. So it comes typically a developed torque. For calculation of developed torque, number of turns per it's Ns equal to phi EB upon Nm Kw BGL RO plus into Ns PP into omega, and developed torque is T the peak equal to Nm Kw BGL RO and SPP and Ns into LP. So calculation of winding parameter Kf equal to fill factor, that is Z conductor per slot. So slot current is equal to Is equal to TD peak divided by Nm Kw BGL RO NSPP, and peak slot current density Jc equal to Is upon Kf into As, and area and diameter of the wire is AW equal to As Kf upon Zs, and where the dW is under root 4 into AW by pi. And for calculation of temperature, if we know m equal to mass and s is specific coefficient, so thermal capacitance of the motor is Tc equal to mcu into sc plus ms into sst plus mr equal to rs and plus m into ssm. So temperature rise of the motor is T rise of motor equal to wcs into T divided by Tc, and temperature rise of the winding is T rise winding equal to wcu into T divided by mcu into sc. So coming to typically net torque, T net equal to half pi square dl upon d theta plus half pi square dr upon d theta plus ni d phi upon d theta. There is a reluctance torque and Cogging torque and the electromagnetic torque component, where L is the inductance of coil, R is the reluctance of the magnetic circuit, N is the number of turns per coil, I is the current in coil, and phi is the rotor position degree. So now coming to Cogging torque in permanent motor, you can see here the figure typically of 2D cross sectional area weave of 2 pole 2 slot PM stator, and you can see here the 2D sectional weave of the 2 pole 2 slot, or in figure 7 flux pattern in the 2 pole aligned with the obtained from 2D analysis. And the Cogging torque, typically you can say what is the 2D sectional weave of a 2 pole motor, and now you can just see how the typically 2D cross sectional weave of a 2 pole slot motor, and is a flux pattern in the slot aligned position obtained from 2D FEM. So now coming to design guidelines for the brushless DC motor. So selection of slot combination, the considered winding has less end turn length and winding loss is lower, and typically efficiency higher, and distributed winding has a higher end turn and winding loss higher and then efficiency lower. So consider winding based on higher winding factor using single layer and double layer, and typically the selection of slot per pole per phase is decided by number 1 the highest winding factor achievable, second the LCM between the number of poles slots should be high to reduce the Cogging torque, and slot per pole combination comes as a fractional or integral, and fractional slot pole configuration, that is Cogging torque magnitude decreases, and not all the magnet edges are near the trailing edge or leading edge of the stator teeth at the given instant. Now coming to selection of magnets for a given rotor bore, the axial length and air gap length, the length of the magnet should be fixed, ensuring PC as high as possible, and also two large PC give the oversized magnet, and for NdFeB and ceramic cobalt magnet PC should be greater than 4, and for ferrite magnet PC should be greater than typically 8 for the same operation. Once the magnet length is fixed, the number of magnets is varied considering the various factors like efficiency, torque, fan, etc. So now coming to typically design parameters aggregation as example, variables normally variable parameters slot per pole per phase, magnet poles, slot fraction, thickness of magnet, air gap length, shaft radius, axial length of magnet motor and remnant flux, and constant is current density and permeance coefficient, and permeance parameter is efficiency and torque. So now coming to design guideline for brushless DC motor, with the start we come to efficiency loop. So fix the specification magnet and select the variables, and then calculate the geometry parameters and magnet loading, calculate the mass of variables parts of the motor, and then calculate the coil turns slot per pole, and of course then calculate the total losses of the motor and efficiency. Then you go to calculate the slot current, resistance, inductance, current density and the electric loading, and calculate the flux density MF drop at various parts. Then calculate the winding temperature, thermal capacitance and temperature. Are the performance satisfactory? If no, you have to repeat, go in the same way. If yes, then stop. Now coming to problems on design of surface mounted BLDC motor, with the example of design with the given parameters. Fixed parameters of surface mounted motor is rated torque 4 Newton meter, rated speed to 2880 rpm, and stator diameter DSO equal to 90 into 10 power minus 3 meter, and axial length is L equal to 200 10 power 3 minus 3 millimeter, and maximum current density J max equal to 6 ampere per minute square, rated power is 1206 watt. So now coming to typically number of slots, Ns equal to 36, number of magnets Nm equal to 12, number of phases 3, and the length of magnet Lm equal to 6 into 10 power minus 3 meter, and axial length is G equal to 0.6 into 10 power minus 3 meter, and rotor outside diameter DRO equal to 54 into 10 power minus 3 meter, and slot opening is 3 millimeter, and maximum flux density is B max equal to 1.6 Tesla. Now stacking factor KST equal to 0.9, conductor packaging factor KCP 0.45, magnet fraction alpha M 0.8, and slot depth factor 0.8, and remnant typically flux density of ferrite magnet Br equal to 0.45 Tesla, and relative permeability of magnet Br equal to 1.05. Now coming to the mechanical speed, omega equal to AR SR upon 60, it comes 301.59 radian per second, and electrical speed is omega equal to Nm by 2 to omega m, that comes 1809.55 radian per second, and fundamental electrical frequency F equal to omega upon 2 pi, that comes 288 hertz, and output torque is T equal to 746 php upon omega m, that comes 4 Newton meter, and number of slots given Ns equal to Nsp into Nsph, that comes 36, and number of slot per pole per phase is Nspp equal to Nsp upon Nm is 1, and number of slot per pole is given Nsm equal to Nspp and ph equal to 1 into 3, that's 3, and the number of slot per pole per phase Nsp equal to Nsp upon Nsm, that is 12 by 12 1, and the coil pole fraction is given alpha Cp equal to integer of Nspp divided by Nspp, that's T tau C upon tau P, that is 2 by 3.667, and then angular pole pitch pi theta p equal to pi upon ns, that comes 30 degree, and angular slot pitch is given theta s equal to pi upon ns, that comes 10 degree, and slot pitch is given theta s equal to pi upon ns, that is pi by 3, and inner stator radius RSA equal to RI plus G, that comes typically to 27.6 into 10 minus 3 meter, and coil pitch is the tau C equal to alpha Cp into tau P, that comes 9.634 into 10 power minus 3 meter, and slot pitch at air gap is given Ts tau S equal to RSI into theta S, that comes 4.817 into 10 power minus 3 meter, and to it that the air gap is given Wt equal to tau S minus Ws, that comes 1.817 10 power minus 7 meter, and distribution factor is Kd equal to sin Ns Pp theta Sc divided by 2 Nssp sin theta e, and Kd equal to, typically putting a value it comes 1, and pitch factor is given Kp equal to sin tau C upon tau P into pi by 2, or Kp equal to sin 360 by Ns Nm by 2 into 0.2 CVS, where NCSC NS by 2 for double layer, NCS equal to NS for single layer. So here now pitch factor Kp equal to, putting a value, it comes 0.866, and Kp, that's typically then skew factor Ks equal to 1 minus theta Sc by 2. So considering SC factor as unity, the flux compression factor C phi equal to 2 alpha m upon 1 alpha m, it comes 0.889, and that permeance coefficient Pc equal to Lm upon G into C5, putting a value, it comes 11.249, and magnet leakage factor, that is KML equal to 1 plus 4 Lm upon pi mu r mu l alpha m tau p into logarithmic 1 plus pi G upon 1 alpha m into tau p, and putting value, it comes 1.1372, and effective air gap is now Gc equal to G plus Lm upon mu r, it comes 0.0063, and Kc equal to, in bracket 1 minus 1 upon tau s upon Ws, in bracket 5 Gc upon Ws plus 1 in minus power 1, and putting value, it comes 1.057, and air gap area equal to H equal to tau p 1 plus alpha m L divided by 2, putting value, it comes 2.601 into 10 power minus 3 meter square, and air gap flux density Bg upon C pi upon 1 plus mu r Kc Kml upon Pc into Br. So putting value, it comes typically 0.35965 Tesla, and air gap flux is phi g equal to Bg into Ag, putting value, it comes 9.3545 in 10 power minus 4 Weber, and typically back iron width is Wbi equal to phi g upon 2 Bmx KSTL, and Wy, putting a value, it comes 1.624 10 power minus 3 meter, and truth pitch is WTB 2 upon Sm into Wpi, putting value, it comes 1.0826 10 power minus 3 meter, and stator back iron radius is given RSB equal to RSO minus Wpi, putting value, it comes 43.376 10 power minus 3 meter, and rotor inside radius is given as Ri equal to Ro minus Lm minus Wpi, putting value, it comes 19.376 into 10 power minus 3 meter, and slot bottom width comes WSP equal to RSB theta s minus WTB, comes putting a value 6.4865 10 to the power minus 3 meter, and slot width inside SU is WSI equal to RSI plus alpha SD WTB in theta s minus WTB, that comes equal to 3.884 into 10 power minus 3 meter, and the slot fraction typically inside the SU is alpha s equal to WSI upon WSI WTB, putting value, it comes 0.782, and slot depth is given ds equal to RSO minus Ro minus G, putting value ds comes 15.766 into 10 power minus 3 meter, and conductor slot depth is given as d3 equal to ds minus alpha s dWTB, it comes after putting value 14.91 into 10 power minus 3 meter, and the SU depth comes as a d1 plus d2, that is equal to alpha dWTB, putting value, it comes 0.866 10 to the power minus 3 meter, and conductor slot area is given as as equal to d3 in bracket theta s into RSB minus d by 3 by 2 minus WTB, and putting a value as comes 7.73175 10 to the power minus 5 meter square, and number of turns per slot is ns equal to integer of PMX upon Nm Kd Kp Ks Bgl R Ro Ns Wm, and putting a value of this Ns comes 18 with round off, and then peak back EMF max equal to Nm Kd Kp Ks Bgl Ro Nsp Ns omega, so it comes like 109.56 volt after putting the value, and the peak current Ls equal to of the slot is tau equal T divided by Lm Kd Ks Kp into Bgl Ro Nsp, putting a value this, it comes Is equal to 198.1924 ampere, and then peak slot current per phase is IPH equal to Is upon NPH Ns, that comes 3.6702 ampere, and peak conductor current density Js equal to Is upon KCPS As, putting value, it comes like 5.696 ampere per millimeter square, and peak slot flux density Bs max equal to mu0 Is divided by Ws, it comes 0.0833 Tesla, and slot resistance is given as Rs equal to rho Ns square L upon Kcs into S, it comes 0.031847 ohm, and then end resistance R equal to rho Ns square by Tc upon 2 Ks Pks equal to 2.409 into 10 power minus 3 ohm, and peak resistance given phase resistance given RPH equal to NSP in bracket RS plus RE, putting a value it comes 0.411 ohm, and then the air gap inductance is LG equal to mu S NSC square mu R mu 0 L tau C KD divided by 4 in bracket LM plus K mu KC into KG, putting value it comes LG equal to 3.0893 10 power minus 5 Henry, and then the slot leakage inductance LS equal to NSC square in bracket mu 0 D 3 cube L upon 3S plus mu 0 D through L divided by WS plus WS by 2 plus mu 0 D1 L divided by WS, and putting values it comes LS equal to 1.00727 into 10 power minus 4 Henry, and the end turn inductance LG equal to NSC square mu 0 tau C by 8 into logarithmic tau C square pi upon 4 AS. So it comes after putting value minus 1.25395 into 10 power minus 8 Henry, and the phase inductance LPH equal to NSP in bracket LG plus LS plus LE. So putting value it comes like LPH equal to 1.3115 into 10 power minus 4 Henry, and then coming stator steel volume, the VST equal to in bracket pi RSC square minus RIC square minus NSS equal to LKST, putting value it comes VST equal to 2.1331 into 10 power minus 4 meter cube, and ohmic power loss PR equal to NSPH IPH square R, that comes PR equal to putting value 16.0689 watt, and core loss given as PC equal to VST PBI rho into Bmax Fe, so putting value it comes to 10.95 watt, and then efficiency that is T omega m divided by T omega m plus PR plus PC plus PS, putting value it comes 93.12%, and slot density, heat density is given QS equal to PR divided by L in bracket 2D3 plus WS into NS, putting value QS comes 63.50 watt per meter square, and slot heat density QST QR plus PC divided by 2 PR RSOL, so QST is putting value it comes 487.19 watt per meter square, and this is typically simplified MEC of surface mounted permanent brushless motor in figure equivalent circuit and simplified of BLDC. And now with this we come to problem on design of surface mount. So question was remnant flux density in sodium cobalt magnet is given in the range of 8000 to 11600 millitesla, and relationship between magnetic flux density and the magnetic field strength H is, the answer is C, mu 0 equal to B upon H, and the remnant flux density of neodymium iron boron magnet is in the range of D, that is 10,000 to 15,000 millitesla, and the range of remnant flux density in ferrite magnets is your 1000 to 4000 millitesla. And question 5, among the radial component of the air gap flux density distributions, so below which one curve is represented there is typically the B, and the among the radial flux component air flux density distribution below which curve represent the D axis flux, typically the C. And question 7, which one of the following slot combination will be the most efficient to use perspective to lower inverter switching losses? DC motor with rated speed of 3000 rpm, typically comes here 6 slot per pole per phase, and NS equal to 120 upon P. So for F equal to 6 slot per pole 3000 rpm, F is typically 100 hertz. And for the following interior power magnet combination, what will be the approximate flux distribution? It's shown in the typically as a B closer to sinusoidal. And for the question 9, for the circumference magnetized stator shown here, the axis 1 and 2 represent, and typically Q and D shown as a B, and these are the references which we have followed to develop material. You can go through, and thank you very much.